We begin the expert talk and keynote addresses by Mr. Rajiv Sharma, Chief Technology Officer, Grid Dynamic, a NASDAQ-listed company in the Silicon Valley that builds enterprise-scale intelligent digital platforms. Mr. Sharma has more than 25 years experiences of leadership and management. He has served in combat role as Lieutenant Colonel in the Indian Army and also as a senior rocket scientist and the first deputy project director of Agni 3 missile program of Defense R&D Organization in India. He was awarded Scientist of the Year for his work in Agni 3 solid rocket propulsion system and also recommended twice for distinguished service at the national level. Mr. Sharma is an alumni of Massachusetts Institute of Technology, Sloan, Harvard Kennedy School of Government, and BIT Mesra. He did masters in space engineering and rocketry in 1987 to 89 from BIT Mesra. He also has got distinguished alumni recognition by the Rocketry Department of BIT Mesra. Today, he will be sharing his expert talk on a blueprint of architecting a large-scale intelligent digital platform to enable climate-resilient agriculture and disaster management. I welcome you, sir.
Yeah, thank you. Thank you, Priyanka, for that introduction. I hope you can hear me all right. Okay, thank you. Every time I listen to my introduction, I get very embarrassed. It's an honor to serve the country, and I don't think I've given back enough. But I did serve for 16 years, and I'm very privileged and proud of that service. The amount of love I've got from my countrymen and the women of our country has been very overwhelming. So thank you for that introduction. I would also like to thank the organizing team of Leeds Connect and the Department of Remote Sensing at BIT. I wish I could be there in person. It would have been awesome to sit in the outer cafeteria again and have coffee and tea and spend the long hours. So I have very fond memory of BIT Mesra and my years. My wife also is from BIT Mesra. So, my special appreciation and a big thank you to Dr. Alok Mukherjee. He has worked tirelessly to coordinate with me. And a big thank you to him for making this happen. Today's talk, this is we are all far away from one another, and had we been on in face to face, it would have been a different kind of an interaction. But I did put few thoughts on a few slides, and I promised you they are not more than 5-6 slides, because all good ideas can be presented in a very few slides. So let me share my screen and let me know when you can see my screen. Can you see my screen? Okay. So, I'm trying to take, as a practitioner of systems, bringing the hardware to the launch pad, I thought I will take a view which is slightly different from a pure technology lens, right? I mean, that one would take from a pure technology lens. And when I looked at the topic as I was preparing for it, I'm not a domain expert in remote sensing, but as a practitioner of systems architecture, product design, product engineering, digital platform engineering, I thought it would be good to take an outside-in view and a structural view, a constructionist view of this important topic for building climate resilient architecture, agriculture, and disaster management, and treat this as a system. Now, when you think of this as a system, immediately you will realize that it's just not about technology. The moment you add the term climate resilient agriculture and then add disaster management to it, numbers that Mr. Navneet was about our country's metrics around population, food consumption, food security, you immediately realize that there are so many hidden elements in actually making the benefits of technology have its actual impact on the people and on the country. especially given the diversity of India as a country and its vastness of the population and the different climatic conditions across the country. So as I look at resilient agricultural operation, and I try to avoid every data that you could easily Google. So I'm just trying to stick to some initial nuances and I'll get into the meat. So a resilient unit is anything that has the trait where it can avoid and reduce any physical and financial damage compared to a conventional farming unit that uses conventional practices. And then it can recover rapidly, and then it's more easily able to adapt to future challenges presented by climate change. And there is a reference, and I will share these slides with Dr. Alok, and it can be used. Now, the important piece is, as you know, agriculture is not a simple business, and it's a good playground for machine intelligence, given the topic of the day. Now, as again, Mr. Navneet had mentioned, there are so many different complex interactions happening at so many parameters on the left: the soil, the crop, the livestock, the weather, finances, markets, regulations. And then on top of this existential, you have where the temperatures are rising, and that leads to variable patterns of precipitation. And then that's where the importance of measuring, predicting, understanding, optimizing of whether it's the nature of the soil or any image from the satellites that you may get for a landmass or a changing weather pattern. You may get understanding of financial side of the business in terms of predictions of the demand and supply, and the stresses in the demand supply systems of crops, and then its impact on the livelihood of the farmers. Again, given that the fact that the farmers in India don't have very vast tracts of land. So all these pieces are amenable to prediction by using algorithms of classification, prediction, optimization. And the whole idea is to create some early warning system that can be used to improve on the resiliency factor of our farming systems. Now, the reality is, no matter what the business use case is, the models are a few. So basically, few machine learning models, few AI models, but infinite use cases. You could use, you would either classify, or you would predict, or you would optimize, or you would process some reports which are in natural language using deep learning, or you may use other statistical models. The model, again, if you try to look at the ecosystem, there are 4 or 5 archetypes of algorithms which can handle more than 80 to 90% of all the use. Should be able to handle many data sources, many data. And for simplicity, consider the space aspect as a data source. You get satellite series, you get a weather pattern, data. You may get a different ideas. How do you process this data? How do you pick up the right features? How do you pick up the right the independent variable? Find out its impact on the dependent variable, and then of course make sure that all these models are pertinent. They are not overfitted. And the choice of algorithms, whether you use a deep learning model or a statistical model, it depends on the type of the problem, would depend on the appropriate amounts of data in different formats, and of course your compute and storage resources. And I don't think there is any challenge in these areas, but the challenge is, it's not about the model where the challenge is. These are 500 lines of code with the built-in, processing pieces around error reduction and hyperparameter tuning, which are all pretty much understood even in the academia and in the research circles. The real challenge on hand is about resiliency and the management of disaster, which is all about what do you do with the output of these algorithms, right? And that is where you soon realize that it is not just the output of the algorithms, it is the complex interaction between the system of systems. I mean, from a structural systems view, there are multiple stakeholders, and don't forget, all this gets aggravated by the scale of the country, right? So there are complex interactions. The moment you talk about artificial intelligence, machine intelligence, human-machine interactions, the first thing you realize that you would be a data guzzling entity, right? Because to train machines to learn from historical data or through unsupervised or supervised learning, you need different types, different formats, different temporal and spatial distributions in data, so that your models learn in a very generalized manner. And I'm not going to get into overfitting and generalization, but I'm sure our audience here understands that. The important piece is now you have multiple systems, and each system has its own nuance, its own resource needs, and its own way of working. And as I said, the scale complicates a lot of things. So now you will have data sources, you will have data providing agencies, you may buy data from the space technology, from the geosensing, remote sensing departments of the government. You may buy data from private agencies. You would then have NGOs and grassroots organizations trying to educate the farmers to how to consume this information and running different sessions, workshops at the ground level. You may have agri-tech startups universe. Leads Connect is one such enterprise which is way beyond a startup, and it is actually making a difference. And I'm sure, I don't know too much about Leads Connect as of now, but I'm sure it is making a big dent in this ecosystem. Then there are funding agencies from the private and the government sector, and then there are public policy organizations, government bodies, and academia. And then there are research organizations, and that research may happen in academia. And again, it could be a public-private funded research. And then not to forget the small, medium, and large technology companies that build products, platforms, and services, and design an ecosystem for consumption of the output of such intelligent systems. So you soon realize that the moment you talk about climate resiliency, you actually elevate the whole dialogue to a very different level, where it's just not about the algorithms, which is not trivial, but it is not the only factor that is going to change the game. And in my mind, when you have a large distributed system, there are many patterns in the industry. When it comes to the industry patterns of how do you handle large distributed systems, where you may have a lot of local data being collected around the local realities, local climate conditions of different regions in the country. And I'm specifically talking about India. And then you would like to have a central nodal agency that can have some kind of a governance and control on the system. So at the regional level, you may have local NGOs and local panchayats and local units that may look at dashboards, help in data collection, help in managing data quality at the source, and help in setting up infrastructure at the edge, especially when it comes to sensors and IoT devices, to make sure that they serve as a good data collection platforms. Now, then at the central level, you definitely need the overall architecture vision. You would need to design the experience of how people are going to interact with this system. It is just not an engineering problem. It's an experience and human-computer interaction problem. And then it will help if you create a logical data model at the centralized level that would be followed at all regional nodes, so that your models and the features that are used to train these models, there is some standardization and some kind of a semblance of sensibility in how these models are trained. And then the central database that will log a lot of happenings at the regional level, and there would be central dashboard, central reporting for different agencies who are funding such initiatives through public-private partnership. and and the aspect of managing these partnerships at from the central and the regional levels with lot of autonomy. You cannot run such public-private partnership through diktats and approval and licensing system. It has to be transparent, and it has to have the elements of decentralization, where the data is centralized, some model architectures and feature engineering is centralized, and which is reviewed from time to time, and there is enough interaction across the regions and the central nodes, so that this entire system, system of system is actually pertinent to the problem of climate resiliency that it is trying to solve. And again, in the end, it's all about downstream consumptions by the farmers, by the people who are engaged in the financial services, who are lending and giving credits to the farmers, people who are leading advisory services, people who are supporting the API ecosystem in this entire hub and spoke interaction model. Again, it is not trivial. There are multiple stakeholders, and each stakeholder has their own modus operandi. So it needs a lot of management overhead. It needs different skills across the gradient, just not about AI engineers and full stack engineers. It's also about program managers, leadership at directors and senior levels, down to the grassroots. And again, the grassroots has to be empowered, and the metrics collection, the efficacy of the entire system measurement, and how much of resiliency is being built, is being increased, how much of flexibility is being given to the farming entities, how much of wealth is being generated, and how much of future proofing the farmers are seeing because of the adverse climatic events, which are only going to increase with the changing climate scenario. So again, it's a you're not going to get this a simple socio. You'll realize you're building a socio-technical economic system. The sociology of the farmer environments and its integration with how they consume the technology, and how the technology enables an economic system to flourish. That is where the actual climate resiliency will thrive. Otherwise, it will become very local, where wherever there is a reach and accessibility, people will have access to it. It will become some kind of a access-oriented system rather than being a national mandate to improve a country's climate resiliency and disaster management capability. So, from the perspective of a practitioner, I would say that imagine you have a large number of data sources from all the nodal sensors. You have large data sources from different space-based platforms that is sending you satellite imagery and other data, and you may have IoT data. You may have image data where pictures are being taken of farmlands, vast tracts of lands, and where you are also able to store this in some form of a raw format, which typically will happen in a data lake scenario. And it doesn't matter whether you build this data lake on cloud. Today, you have enough technologies, like some of you may have heard about Kubernetes engines, where you can even build a good orchestration models and deployments, infrastructure, even on-prem and in a hybrid manner between on-prem and cloud. And then your reports can run on a data warehouse, which will hold historical data, which is very much cleaned and transformed to make sense for the people consuming reports. And whereas the data lake, which is having all the raw data in different formats of image, voice, vibrations, pressure, temperature, humidity, soil pictures, and pictures of different temperature profiles during the day, month, all those seasonalities, all that can be stored in data lake kind of a entity. And then you could, with experts, you could at the central hub, you could decide on what kind of features would be the best explanatory variables to define the dependent behavior of the dependent variables. And whether, as I said, right, no matter what the problem, you will use a very few model archetypes. You will either classify, you will predict, You may have time series data. You may have language, semantic, natural language reports. You may have to optimize on cost or optimize on revenues or financial outcomes of a particular decision. All those scenarios ultimately can be captured under these 4 or 5 archetypes, and then you need to create a kind of a system where all these models are running and are trained on local data in a very autonomous manner. We call them MLOps pipelines, which is non-trivial. Again, you need skilled resources, trained people to set this up, and once set up, it's much easier to govern and manage the model training, to make sure that, and model evaluation, and then maintaining a feature store of all the data that is used to train the model, making sure that you maintain the versions of all the feature stores, and I have IDs which model gave what kind of output. And then you may have an anomaly alert, you may have some outliers, you may have some next best action, you may have some recommendation engines, prescriptive engines, you may have some general information to be sent out through APIs, and then that is where the digital API economy to go to the last mile will matter. And if you look at this entire fabric, there are so many stakeholders, and there is so much of interactions that is needed, and human leadership is the key. I've seen such initiatives fail at many large organizations, not because of technology, but the human side of technology, right? So the human side of technology is essential, and that has to be managed, and the right decisions, right amount of autonomous processes should be designed into the system. And again, when you're looking at the fabric of the system, how do you look at the public-private partnerships? How do you look at the agri-tech scenario? How do they partner with the government? What subsidies, what support they get from the NGOs and the government? What is the level of grassroots leadership? The villages with poor leadership at the grassroots should not suffer. So how do you create this distribution of information in a very fair manner? That is where the policies of the government through state and central initiatives will matter. How do you ensure platform stability? How do you ensure business continuity, disaster recovery, fault tolerance? Which is why when you design the front-end systems, when you design the algorithms, you put them in containers that even if they fail, the new containers would be spun up automatically through automation of the infrastructure, which we normally call software-defined infrastructure. Again, it needs good engineering, thoughtful systems design, thoughtful systems architecture, giving enough thought to the illities of the system in terms of maintainability, scalability, stability, and not to forget the automation aspects of automated training, building DevOps teams at local level in the nodal centers, building these teams in the centralized hubs in different regions, maybe. And then how do you interact with the data strategy? What is your data strategy at the nodes? What is the data strategy at the hub? How do you persist this data in a very centralized manner that it can be consumed to train all the machine interfaces, and then making sure that the evaluation, the models are evaluated and the outputs are trustworthy, so that the right decisions, either autonomously, which the machines are taking, or if the machines are working as assistants to humans in the loop, that entire experience is designed appropriately. So, as I said, the very topic, I wanted to leave you with more questions, and I wanted to leave you with a lot of food for thought, that it is not just about most of these models, like deep learning models, they're not more than 600 lines of code. They're available open source, but the key is the data. The data is the operator, and the data is the operand. It flows through the system, it trains the system, and it's just not a passive entity anymore. So the whole country actually has to be a very data alive nation. And every element at the node, whether it's an agri-tech, a government research body, academia for really doing research in this important area of climate resiliency and disaster management, you will have to think from the problem, then look at where the data is available to help you answer the questions to that problem. And then how do you train these models? And how do you consume these models? And then how do you distribute the learnings from these models? And how do you do this at scale all the time, every time, with correctness, with consistency and reliability all the time? And how do you make sure that this national treasure for building in a country which Mr. Navneet said, there are 58% of the population is engaged in this activity. And this is something that has to be done as a national effort. And I'm sure India is moving in that direction. The way the country's GDP is growing, the way our economic prowess is growing, the way our voice is heard in the international forums. And I've been to many of these forums, both in India and the US, because of the profession I had. And I can tell you that India has a lot of capacity at the grassroots, and that is the strength of a nation. We have the depth, we have the width. With the right leadership and the right vision, I'm sure climate resiliency would be much easier in a nation like India, where there's such a vast talent pool, engineering, management, and even in fact we could use our armed forces also as data collection units. We have the territorial army, we have the home guards. A lot of this manpower, when we are not occupied in defending through external conflicts or internal conflicts, can be force multipliers in making our country as a data collection, strategic data collection nation to drive such disruptive initiatives, and we could become an example for the entire world. Thank you for this opportunity. I enjoyed actually preparing for this. I did not know much about climate resiliency. I've been to many forums, but this was wonderful. And my view, I took this view of a practitioner's view. How do you make this happen at scale, where thousands and millions of people are involved in putting this, cross-functional systems together? So thank you for this opportunity, and I'm ready for questions.